Yeah, it is interesting how the fall semester we don't have a spring break, and it's fine somehow. But spring without spring break just seems like cruel. Just seems just part of the academic rhythm. Never, never. That's right. Learning before fun, knowledge before whatever it is you guys do on spring break. All right, so let me get back to our sharing. Obviously, I don't have your exams done yet. I'll have those done certainly no later than Tuesday. I may post the results before then and maybe just make a video going over the exam so we don't have to wait till Tuesday. We'll see how that goes. So stay tuned for that. But in the meantime, we'll continue on with optimization methods. So last time we discussed the method of steepest descent, and that's when I was doing my little robot thing, looking in different directions, finding the steepest descent direction from the gradient, going in that one direction, basically a one-dimensional minimization problem, find the valley in that one direction, go there, and then redo steps 1 and 2. So we want to now look at Newton's method, which we, of course, already know, and we've seen before in the context of root finding. So there won't be anything new per se in terms of Newton's method. However, we're now applying it for a different purpose. So we're applying it to find extremums rather than roots. So as I've mentioned before, there's a subtle difference there, but not one that ultimately changes Newton's method at its core. So Newton's method, great. So it's in some sense better, which I'll show you, better than method of steepest descent. It's very similar in the sense that it's this two-step process, which direction to go and how far to go in that direction. Is just how you answer those two questions now is going to be a bit different. But the idea is that it's faster. It will converge faster. All right, but basically the connection between extrema and roots is the fact that if I have a function f of x and I take the derivative of it, the locations where the derivative is 0, of course, are the minimums and maximums and the stationary points. So therefore, the roots of f prime of x are those maximums. So before we found the roots of f of x, now we're going to be finding the roots of f prime of x. So basically, everything's just going to get upgraded. So all the f's are going to be f primes, and all the f primes are going to be f double primes. And that's essentially it. And we're done with Newton's method. But I'll drag it out ad nauseum and make it seem much more complicated than it really is, just for the sake of confusion. Well, I hope not. So this really is the workhorse of optimization algorithms. Many, many, many optimization algorithms at their core is a big honking Newton's method. There are lots of potential pitfalls. There are lots of potential situations that can arise, but at their core, Newton's method really is the workhorse algorithm for these optimization problems, as well as, of course, root finding as well. So it does have quadratic convergence rate, just like it does in the root finding context. So that's fast, but you need a relatively close initial guess in order for it to get where it wants to go quickly. So again, if you can plot it, which isn't the case for multidimensional cases, but in a 1D case, you can plot it, you need to be in the correct bowl. So if you start in one bowl, you're never going to jump out of that bowl into another bowl and find that bowl's minimum. So you have to have an initial guess that is somewhat close, or at least in the same bowl as the minimum that you're seeking. So if we have a single objective function, so just an f, and then we have n design variables, so x1 through xn, that can be converted into a system of n nonlinear equations by evaluating the gradient. So let me say that again. Single objective function, that means 1, of n variables is going to be turned into a system of n nonlinear algebraic equations that we need to evaluate. Now, we already know how to do that because we learned in section 5.5 how to you apply Newton's method to a system of nonlinear equations. So we already know how to do that. Let's just see how we do the conversion. So the conversion is done like this. So we have our f of x1 through xn, that's our j, that's our objective function. If we differentiate j, our one function, or f, whichever way you want to look at it, if you differentiate f with respect to each of the design variables, then you get n equations. So we'll call those f1, f2 through fn. So f1 will be partial f partial xn, so partial f partial x1 is equal to 0. f2 is partial f partial x2 is equal to 0. So we're turning one function f, that is a function of n variables, into n functions of those n variables when we take the derivative and set them equal to 0. Once again, then these f1, f2 through fn's, those are going to be nonlinear algebraic equations. So we already know how to solve those using Newton's method for systems of equations. So that's going to be the basic approach. So whenever you think of optimization, minimums and maximums, when you come out of calculus class, it's just take the derivative and set it equal to 0. Everything we're going to do today is exactly that. It just looks more complicated because we have more variables. Instead of f of x, it's f of x1 through xn. And ultimately, we could have multiple f's. So it's going to look more complicated, but in the end, it's exactly the same. We talk about gradients. We talk about Hessians. Gradients are just first derivatives. Hessians are just second derivatives. So everything we say about first derivatives and second derivatives for f of x, so slopes and curvatures, that all carries over conceptually to Jacobians, which are all the first derivatives, and Hessians, which are all the second derivatives. So just keep that in mind. We're just kind of, again, upgrading everything from what it is in calculus for one function of one variable. All right, so we get our n equations. These are nonlinear algebraic equations. If I differentiate the one objective function with respect to each of the design variables. Now, alternatively, we can look at this a little different way. In the end, it's exactly the same. In the end, we'll have the same algorithm, the same equations, but again, just to confuse you, we can look at this from a slightly different alternative point of view. So if you don't like this, that's fine, just ignore it and just think about it the way I just explained it. And the two will come together in the same thing, and then we'll move forward from there. But let's look at it in a more direct way by using a vector form. So again, we want to differentiate the objective function. And what we did before was do that first. And then in doing so, we converted our single objective function into a system of nonlinear algebraic equations. And then we, if you look back at section 5.5, Newton's method for a system, then we use Taylor series on each equation in order to get our system of linear algebraic equations that we then solve to get the step sizes. So that's kind of the process that we went to. Differentiate, set equal to 0. We get our system of nonlinear algebraic equations. We use Taylor series on those to linearize them. And then using those linearized algebraic equations, which is just a big system of equations for the delta x's, we can then solve for the delta x's. And that's the first step in Newton's method. Instead, we're going to just flip the order. So instead, we're going to first take the Taylor series. So now it's going to be a multi-dimensional Taylor series. It'll be in vector form. So we first take the Taylor series of the objective function, and then we evaluate the gradient. And of course, the gradient is all the first derivatives. And then that will produce the same linear algebraic equation system that we then solve for the step size. So we're just reversing the order of the differentiation through the gradient and the Taylor series. So this is what it looks like. So again, we have a single objective function, but it's a function of n design variables. So j is f of x1 through xn, just like before. And we're going to indicate the x's by the vector x. So this is a bold x, so that's the vector of all of the x's, but it's still just one function. Then the Taylor series of this objective function about a point x, the vector x at some iteration k, is going to look like this. So this is just a vector form of the Taylor series. So f at a vector x is f at k, our reference point, so that's xk, plus delta x times the gradient of f. The gradient, again, is the first derivatives, plus a half times delta x times the gradient of the gradient. The gradient of the gradient is the derivative of the derivative. That's the second derivative. And so that is simply looking at, again, first, so no derivatives here, first derivatives and second derivatives. So there's some shorthand here. Fk really means f evaluated at xk. And again, k is the iteration number. So k is going to start out 0 for our initial guess, and then increment by 1. So k will be 0, 1, 2, 3, 4 until it converges. Then we have the gradient of f, which is really the gradient of f at xk. Then we have the gradient of f, which is the Hessian. So the gradient is the derivative of the gradient, which is the derivative. So that's the derivative of the derivative is the second derivative, and that is the Hessian. So gradient for first derivatives, Hessian, which I'll show you in a moment, for second derivatives. And then again, the delta x is the step size. And now, but now it's a vector. So there's a delta x1, delta x2, delta x3, through delta xn that are all being updated as we go. So here's what the Hessian looks like. It's just a matrix of all the possible second derivatives. So if you look down the diagonal, it's partial squared f partial x1 squared, partial squared f partial x2 squared, x3 squared, down to xn squared. So the second derivatives with respect to each of the variables goes down the main diagonal. And then off the main diagonal, you have all the possible other second derivatives. And they're ordered in a normal matrix C sort of way. So this is the 1, 1 position of the matrix, first row, first column. So it's the 1, 1. This is the first row, second column. So x1, x2. So that's partial squared f, partial x1, partial x2. And then the next one would be 1, 3. So partial squared f, partial x1, partial x cubed. Oh, sorry, partial x3. And then the last one is partial x1, partial xn. And then you have the second row. So these are all now x2s, x2, 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 with the second one going from 1 to n. So it's just nicely ordered, so all the possible second derivatives of f with respect to x1 through xn. That gives you this big Hessian matrix, it's n by n, where n is the number of design variables. Now, if f is smooth, so in other words, you can differentiate it nicely at every point, and doesn't matter which direction you come from the left or the right, you get the same value, then the order of the differentiation doesn't matter. So remember from calculus, if f is smooth, then partial squared f partial x1 partial x2 is the same as partial squared f partial x2 partial x1. So in other words, this order doesn't matter. So if that's true, which is usually the case, f being smooth, then this is the same as this. This is the same as this. This is the same as this, this, and so on. And we have a symmetric matrix. So under normal circumstances, the Hessian matrix is symmetric. Okay, that's this first point here. Now, remember the second derivative test? That was basically checking curvatures. So in the 1D case, you find where f prime is equal to 0. So that gives you all the 0 slopes. All of those are candidates for an extremum. And then to check whether one is a minimum or a maximum or neither, you check the second derivative. So you check the curvature. Is it concave up, concave down, and so forth. Now, all those second derivatives are contained in the Hessian. So from the Hessian, then, we can apply the so-called second derivative test, basically the curvature, to determine whether we have a minimum, a maximum, or neither. And the way that works is based on the eigenvalues of the Hessian. So if all of the eigenvalues are negative, then we say that the Hessian matrix is negative definite. In other words, the eigenvalues are definitely negative. In that case, we have a local maximum. So again, that's like concave down. So that's like the curvature being negative. If all of the eigenvalues are positive, then so it's positive definite, the eigenvalues are definitely positive, then our function has a local minimum. So the curvature is positive, so it's a local minimum. Great. If it is such that we have both positive and negative eigenvalues, then we have what's called a saddle point. A saddle point's like a stationary point. Remember, in the 1D case, that was a flat spot in the curve that was neither a maximum or a minimum. So it was a flat spot. So a saddle point, think of a saddle on a horse. If you look at it from the side, it goes like this. If you look at it from the front, no, wait. If you look at it from the front, it goes like this. If you look at it from the side, it goes like this. So a saddle point in 3 dimensions is like that. So it's a point that has a zero slope in all directions, but it's neither a minimum or a maximum. So that's the case if we have both positive and negative eigenvalues. If the Hessian matrix is semi-definite, which means that at least one of the eigenvalues is 0, then actually the second derivative test is inconclusive. So that's like the curvature being 0. If the curvature is 0, then you don't know it. It doesn't tell you whether it's a maximum or a minimum. All right, so the point is the Hessian tells you all that information from the second derivatives. Okay, so let's then, again, they converge either way you do it, whether you do Taylor series first and then take the derivatives, or take the derivatives first and then the Taylor series, you end up with the same thing. We want to evaluate the first derivatives, that's the gradient, of our f of x. Now remember, x is a vector, so we have to take the derivative with respect to each of the design variables. So we have a partial f, partial x1, partial f, partial x2, 3, 4, all the way up to capital N. So the way we write that in vector form is the gradient of f is equal to the 0 vector. So the gradient of f is all the first derivatives of f with respect to each of the design variables. So again, in our direct analogy to the one-dimensional case, this is literally just saying, where is the derivative equal to 0? Where are all of the derivatives now equal to 0? So our vector form of the equation looks like this. We have the gradient of f is equal to the gradient of f evaluated at xk plus the Hessian evaluated at xk times delta x at xk. And then we set that equal to 0. So what we're doing here is we had our Taylor series for f, but now we've differentiated it. So the gradient of f equals the gradient of f at k plus the Hessian, which of course is the gradient of the gradient of f times the step size. We set that equal to 0. Once again, we've truncated the Taylor series after the first 2 terms. So now, by setting this equal to 0, this we know, because we know all the f's, we just evaluate them at each of the xk's. So that's the right-hand side of our system of equations. We know that, so it's now minus because I brought it over to the right. And then we have the Hessian, which I also know, that's just all the second derivatives evaluated at my current set of points. And then the unknowns are the delta x case. So this equation 6.6 is now a linear system of algebraic equations where I know the Hessian. It's just a bunch of numbers now because I evaluated at my current approximation, at the kth approximation. The right-hand side vector is all these gradients. Again, all just numbers because I've evaluated the gradient at each of the current values of x. And then I'm solving it for the delta x, the step size, all of them. So I have a system of linear algebraic equations for that step size. Now you think, how does this relate back to the original? So here's the original Taylor series as we had it for root finding. It was delta x equals minus f of xk over f prime of xk. So notice, everything's just been upgraded in derivatives. So now I can't divide by the Hessian like we do in the scalar case here, but this is my second derivative now. Notice the first derivative gets upgraded to a second derivative, and my function evaluation gets upgraded to the first derivative. So this is just the gradient version of this, essentially. Still Newton's method to get our delta x's, but because I'm now looking at the roots of f prime of x, the gradient of f, now this function evaluation becomes the first derivative, this first derivative becomes the second derivative. And that's all. Once you've done that, you have your delta x's. You just update the previous approximations for x, which is now a vector again instead of just one value, but nevertheless, you just take your vector of x's, you update with the vector of delta x's, and that gives you a new approximation for your x's at the next iteration, the k plus first iteration. So it's just more of the same. The process is exactly the same, iterate, iterate, iterate. Now, every time you do this though, your right-hand side vector changes. The gradients of f don't change analytically, but the values of the gradients change as you change your values of x. Same thing with the Hessian. The Hessian analytical evaluation of the second derivatives of all of the f, those don't change. But when you evaluate those at the particular x values at your current approximation, then they just become numbers. So you have to update the matrix and update the right-hand side vector every time at every iteration. And then you solve that system of equations for delta x. Once you have a new estimate for delta x, you reevaluate the gradient on the right-hand side, the Hessian on the left-hand side, and then you solve that new system of equations for the new set of delta x's. But again, conceptually, it's no different than this for the 1D root finding case. All right. So some comments. Essentially, this is a multidimensional version of equation 6.1. So if you look back at 6.1, it looks similar to this one, but it's the one that applies when I just have a f of x, a single function of a single variable, but now doing optimization. So it would look like this. So we have delta x, okay, is equal to minus f prime of xk over f double prime of xk. So if you look back at equation 6.1, which we had for, again, f of x, where there's only one function of one design variable, that was the equation we used to get delta x. So now it's the same, except again, I can't divide because this is a matrix, so I can't divide by a matrix. So I actually have to, so it's kind of like bringing this f double over here. I have my f prime on the right-hand side, f double on the left. So that's my second derivatives on the left, first derivatives on the right, and I'm solving now for a vector instead of a scalar. But again, it's the same basic setup, same basic framework. just a system of equations rather than a single scalar equation. So here's what it looks like if you write it all out. So that vector equation that I just showed you on the previous slide, this is that same thing, just written out. So I have my solution for all the delta x's, delta x1, delta x2, delta x3, all the way to delta xn. The right-hand side is the negative of the first derivatives. And then the left-hand side is the matrix of all the second derivatives, the Hessian. So again, these are evaluated at the current kth iteration. These are evaluated at the current kth iteration. So these are all just numbers and numbers. And then you solve that system of linear algebraic equations for the delta x's. Okay, lots of comments to make about this. So what we're really doing essentially is applying the standard Newton's method for root finding, no different than the previous chapter, but now applying it to the derivative or the gradient of the objective function. That's the only difference. So whereas the standard Newton's method for root finding requires evaluation of the f in the numerator and the f prime in the denominator, it's now f prime in the numerator and f double prime in the denominator. Or again, they're vector forms with the gradient and the Hessian. Once again, whereas the standard Newton method for root finding approximates the function locally by a straight line, in multi-dimensions, now it would be a plane. What's happening is because you're taking now the derivative first and then applying Newton's method, you're actually approximating locally the function as a parabola. So in the root finding case, remember I had this plot, and you pick a point as your initial guess, and you come down along the tangent, that's your next guess. You go up, pick a point, take the tangent down, and then go up, take a tangent down, and you get closer and closer to the root right there. So that is standard root finding. And so you're basically approximating each of these, at each iteration, you're approximating the function as if it was a straight line. Now, by upgrading by one derivative, the straight line becomes a quadratic, becomes a parabola. So we're approximating the f of x as if it's a parabola at each location. Sorry, at each iteration. As for root finding, it works great as long as you have a good initial guess. That's what the next point is. And it does have quadratic second order convergence rate as you iterate. So it's very fast if you have a good initial guess. Again, the root findings carry over to the optimization context wonderfully, perfectly well. Wonderfully, perfectly well. That's terrible English. Newton's method for optimization requires evaluation of both the gradient and the Hessian. So that's, again, first derivatives and second derivatives, as opposed to functions and first derivatives. And so that's a lot of derivatives. And if your functions aren't terribly smooth, then that's a problem. Every time you take a derivative of a not so smooth function, it gets less and less smooth. So if you have a really nice clean function and you differentiate it, you get another nice function of the slopes. Second derivative, you get the nice analytical function of the curvatures. But if it's a not so nice function like you got from experiments or something, and you differentiate, any little issues or inaccuracies in the original function get amplified every time you take a derivative. So in practice, that can be somewhat of an issue. Another issue that comes up is because you're solving a linear system of equations where the coefficient matrix is the Hessian, you have to invert your Hessian every single time. So at every iteration of the calculation of the algorithm, you are inverting your Hessian matrix. So that means, first of all, that has to exist. It can't be singular, so it has to be invertible. And the Hessian is changing every time, every iteration. So you have to evaluate the inverse, not only that, but it has to actually exist. So a common fix for that is to use what's called the Quasi-Newton method. Quasi in mathematics means almost. So if you say quasi-steady, it means it's almost steady. It's not quite, strictly speaking, it's not steady, but it's almost steady. So a quasi-Newton method is, well, it's kind of like the Newton method, but it's not quite exactly precisely the Newton method. The idea in the quasi-Newton method is you simplify the Hessian inverse calculation by assuming or approximating the Hessian matrix using only first order rather than second order partial derivatives. And you say, well, that seems wrong, right? Because they are what they are. But what you're doing is you're saying, well, I don't need the whole Hessian everywhere. I just need it close to where my current iterate for the root is, my current approximation for the root. So you have that approximation. Let me assume that close to that approximation, it behaves like a parabola. And then that allows you to, when you take the first derivatives, that just becomes a linear function. So it simplifies the process, and those approximations change as the approximations change. That's a weird way to say it. So as you iterate, just like with the standard Newton's method, as you iterate, you're getting better approximations for those straight lines close to the root. So it may slow it down a little bit because it doesn't have as much information built into the Hessian itself, but it will make the Hessian inversion process a little bit easier, a little bit less computationally costly. Okay, we're going to sweep that under the rug. We're just going to let MATLAB or Python do the solution for us, so we're not going to worry about that little detail. All right, now everything I've talked about so far has been unconstrained, so no constraints on the optimization. Now we need to think about, okay, what about constraints? We talked about this last time. I need to get across the street to go get my tacos at the Commons cafeteria, but I need to do it in a safe way. So I'm going to walk on the sidewalks because I'm a conformist and I don't want to get hit by a car. So I'm going to walk across State Street at a crosswalk. So those are constraints. Those are constraints on the optimization problem. We can have two types of constraints, equality constraints and inequality constraints, and they're exactly what they sound like. Equality constraints are algebraic relationships between various design variables that have to be satisfied exactly. So they might be geometric constraints, like you need to cross State Street at a crosswalk. You can't do any jaywalking or cross in between intersections or anything like that. So it's a specific algebraic relationship between design variables that has to be satisfied. Inequality constraints are just that. They're algebraic relationships, again, between design variables, but they're now in the form of inequalities. So this is like the rocket engine I mentioned on Tuesday. So a rocket can't have a thrust that's less than 0 or bigger than its maximum thrust. So those are inequality constraints on the upper end and lower end of what the thrust can be. So they have various purposes, various applications in different situations, but in general, constraints are things that must be satisfied. We're not trying to make it so it's close to the constraint being satisfied. The constraint must be, their constraints on the optimization. They must be satisfied, whether equality or inequality. We're going to focus first on equality constraints because they'll draw from the calculus that we already know and love. And then later on, we'll look at how we deal with inequality constraints as well. So let's look at optimization subject to equality constraints. So we have our objective function.
I'm having trouble hearing
you. Alexa would never do that, right? Because Alexa's so much smarter than Siri. So my daughter has an Alexa in her room, and she doesn't understand, and it costs, these Echo Dots, whatever, they cost like $20 or whatever, they're super cheap. So then I go and I get the HomePod Mini, which costs $100. And she's like, well, why would you buy something for $100 that I can get for 20 bucks or 25 bucks? And I said, well, it's Siri. And just like Raj, I love Siri. Have you ever seen the Big Bang Theory episode? It's one of my favorites, one of my all-time favorites, when Siri first comes out and Raj falls in love with Siri. It's great. Anyway, that's what happens when you buy into the Apple ecosystem. You're stuck with Apple Watches, iPhones, iPads, Mac laptops, and iPad minis everywhere. Are they more expensive? Yeah. Are they fundamentally better? You bet they are. At least that's what I tell myself to justify the additional cost. So now there's this new thing, came out during the pandemic several months ago, Apple Fitness Plus. It's actually pretty good. I wish it would have come out earlier in the pandemic. I wouldn't have put on my COVID-19. I get it, yeah. So trying to work off my COVID-19. Anyway, so the problem with it's great. It's really cool. The problem is you need like about 20,000 Apple devices in order for it to do everything it's supposed to do. So you don't have to have an Apple TV, but it's easier if you do. So you have your Apple TV little box hooked up to your television. Then you have your watch, or you could have your watch and an iPhone or an iPad or something. But you have to have a watch because it shows all your stats on the screen. Now, could you do the exercises that they're telling you to do without the watch on? Of course you could, but you would not have the satisfaction of knowing exactly how many calories you've burned, how many minutes of exercising you're getting, how close you are to closing your little rings, which of course is now my measure of. Siri's now talking to me about my rings. Oh, Siri, you should just leave me alone. There's got to be a way I can turn off Siri at the beginning of class, which I forget to do. Oh yeah, there it is. I knew there was. Anyway, so it's great, and it's all integrated together. And as you're exercising, there's a burn bar that shows like how many calories you're burning relative to other people that have done the same workout. So it's kind of cool. But anyway, you have to have like 3 Apple devices in order to really make it worthwhile. So you get sucked into the Apple black hole, which is fine. So I love Apple. I was one of the first ones to buy an Apple Macintosh. What year was that? Anybody? What year did the Apple Mac come out? Anybody remember what decade? What century? What millennium? Does anybody remember a famous, not because you were alive then, but because you pay attention to pop culture, does anybody remember a famous, someone's got it in the chat. They looked it up quick on Google. 90s, probably older than me. Yes, Ramiro, you are correct. It is older than you, and it's not the 90s. So there is a famous Super Bowl commercial in 1984. Does it 1984 sound familiar? Because you all have wonderful English teachers in high school. 1984 was a famous book about how we're going to be living in this post-apocalyptic world in 1984, written many, many years before. I actually don't remember when that was. Yeah, George Orwell, exactly. And so this was a play off of that. But anyway, that's the year that the Apple Macintosh came out. Should I tell them? Because then they can figure out my age. Well, that's fine. If they want to find out my age, they can figure that out on the internet easily anyway. In 1984, I was a freshman in college. So all my friends were getting cars or other fun things. What did Kevin get going off to college? He got a Macintosh. Do you know how many RAM it had? How much RAM it had? What? It had 128 kilobytes, not even megabytes, not gigabytes, kilobytes. It did not have a hard drive, no hard drive at all. So you had a floppy drive. Each floppy drive had 400K. So your operating system, your application program, and whatever file you're working on had to fit on a 400K, K, not M or G, K, had to fit on a 400K drive. Within a couple years, we had this amazing innovation. They had a double-sided floppy disk drive. Woo! 100K, 400 on each side. Now look at your operating system and how big it is. On my phone, whenever I upgrade my phone's operating system, it's multiple gigabytes. So the original Macintosh operating system fit in less than 400K. It was amazing. That's what me and my friends did. I couldn't spend that $1,000 on a used car instead. It was $2,000 for this amazing feat of technology and engineering. Did we have the internet to hook it up to? No, Al Gore hadn't invented it yet. That's a joke, by the way. So no internet to hook it up to. The monitor was 9 inches, black and white. Now, not black and white, it's grayscale, so, but no color. It was an amazing, amazing thing at the time. Okay, so here's why I bring this up. So I've been a Mac fan for years, Apple fan for years. My first programming was done on an Apple II Plus when I was in high school. And I've had Macs of all different sorts. If you come in my office, I actually have kind of a museum of old ones. At home, I have a museum of old ones. But here's the point. So I'm happy as a lark, couldn't be happier. But then every once in a while, some idiot has to write an article about if you would have, instead of buying Apple products, put the same amount of money into Apple stock, how much you'd be worth. And that's when you're like, oh, well, yeah, it's a lot of money. So anyway, yeah, so I spent a ridiculous amount. And then the dot matrix printer. Have you ever seen or heard a dot matrix printer? So these are the kind that go, they take each line, and it's literally a whole bunch of tiny little hammers that push the ribbon against the paper. And they were amazing at the time. It cost $500. So I spent $2,500. Could have bought a car in 1984. Instead, I bought a computer. What a nerd. Anyway, so yeah, I should have bought stock instead of my first Mac, and the second Mac, and the third Mac, and the fourth Mac ad infinitum. Anyway, that's fine. I made all my money now in GameStop, so I'm recovered it all. How long did it last you? So my original one lasted me for, so this is actually interesting. So back in the 80s, computers were so expensive that you had to make them last for quite a while. So that original one lasted me through college and into grad school. So probably about 6 years, maybe 7. Then we went through an era when the prices came down where we were getting new computers every few years because they were much cheaper and they were changing very rapidly. Now we've kind of gone back to the era where there's no need to get a new computer every few years because they really don't change that much. So it used to be, you know, they get a faster processor. Oh, I need a new computer. They get new connections. Oh, I need a new computer. They get a double-sided floppy disk drive. Oh, I need a new computer. You know, now the technology is not advancing very quickly, so you don't need to buy a computer very often anymore. So it's kind of sad, but it's good for my pocketbook. So talk about optimization. That's an interesting optimization problem. How much money to put into Apple products versus Apple stock? I need a Mac so I can access the internet that Al Gore blessed us with so that I can trade my stocks. But I only need one that's fast enough to actually do my online trading. Anyway, okay, so optimization is subject to equality constraints. So the math behind this is called the method of Lagrange multipliers. You may have heard of it, maybe you haven't, maybe you did and you forgot it. If you did, you probably did forget it because you haven't used it very much. But it's very simple. So basically, we now have two things. Before we had one thing. We just had the objective function, which we were trying to minimize. Now we have the objective function and we have a constraint, or maybe multiple constraints. We'll just start with one for now. So the way you combine them is to use what's called the method of Lagrange multipliers. I'll talk about it briefly, and then we'll do an example to show you. It's very, very straightforward. It's really, really slick. It's very powerful. So basically, the idea is you take a constrained optimization problem and turn it into an unconstrained optimization problem, which of course we already know how to solve, because that's what we've been doing for the last class and a half or so. So if I can turn my constrained optimization problem into an unconstrained optimization problem, I know how to solve it. We have all the machinery. So the way you do it is you take your equality constraint or constraints, and that again is a relationship between various design variables. And then what you will get is the optimal solution. Now, this point is addressing how many constraints you can have. If you have as many constraints as you do design variables, then you'll get a unique solution. There's only one solution to the problem. And so in other words, there's nothing to optimize. So in order to have something to optimize, you have to have fewer constraints than you do design variables, so that there's some freedom left for something to change, something to vary, in order for the optimization to really be useful. So we'll have fewer constraints than we do design variables. It might be one fewer, it might be 10 fewer, it might be 1,000 fewer, but whatever, we have fewer constraints than design variables. All right, so let's do an example to illustrate how this works. So what we have is an ellipse. So we have an ellipse, something like this. It has a semi-major, well, actually two, semi-major and semi-minor axes. The semi-major axis is the long one. That's this one. Semi is half, of course. So there's the semi-major axis and then the semi-minor axes as well. So here's the equation for the ellipse. It's the square of x1 plus x2 plus 2 times the square of x1 minus x2 is equal to 8. That's an ellipse, something like that. So if you multiply it out and simplify it a bit, that gives you your constraint. So we'll call the constraint G. It's a function of the two design variables, x1 and x2, which are the coordinates. And it says that the value of x1 and x2 have to be such that they are somewhere on your ellipse. So this is x1 and x2 coordinates, but you can't just have any x1 or x2 coordinates. They have to be such that they together sit on that ellipse. So it's a constraint on the relationship between x1 and x2. x1 and x2 have to be such that they satisfy this equation. Fine, so that's the constraint. Now, what we want to do is find the semi-major and semi-minor axes. So how would you devise an algebraic way to quantify those? Well, the semi-minor axis is the distance to the point that's closest to the origin or the center. And the semi-major axis is the distance to the point that is farthest from the center of the ellipse. Okay, so I need some measure of the distance from the origin here at the center. So we're going to have a distance objective function, J. It's a function of x1 and x2. It's going to be x1 squared plus x2 squared. Now you say, wait. The distance is the square root of x1 squared plus x2 squared. Where I'm going to get rid of the square root, which is perfectly fine. If I find the maximum of the square of the distance and the minimum of the square of the distance, that's going to give me the same result as the minimum maximum distances themselves. But then I don't have to worry about a square root when I do the derivatives and all that. So this is really, so our objective function is the square of the distance from the origin, x1 squared plus x2 squared. Again, squaring is still going to give me the same result. The nice thing about squaring them is now negatives don't matter. So the distance, I don't have to worry about square roots, don't have to worry about negatives. Negatives and positives will be treated the same way. Now, if I don't incorporate the constraint, so if I don't say that x1 and x2 have to be on the ellipse, and if I just take my objective function and I determine the minimum, what's the minimum going to be? Anybody? Okay, this is like the Sunday school question. Have I told you the answer to the Sunday school question? When you're a kid and you're in Sunday school and you fall asleep and the teacher asks you a question, Kevin, just wait, when you wake up, just say Jesus. It's the answer to every question in Sunday school. Do you ever think about that? So this is like that. This is like Jesus. So you're falling asleep and I call on you and you say, what's the answer? And of course, you have no clue whatsoever, but you just blurt out 0, right? That's like Jesus, right? So the minimum is 0. And what's the maximum? Infinite. So if I don't put a constraint on my distance function and I say, well, what's the minimum? I'm just going to say, oh, well, it's just 0. What's the maximum? Well, it's an infinity. So you have to incorporate the constraint, which is a constraint, again, on the relationship between x1 and x2. Does that mean you can divide by Jesus? I knew someone was going to say that. Yes, you can divide by Jesus, but unfortunately, because Jesus is infinite, that is gives you a undefined result. So yes, you can divide by infinite Jesus, but it does give you an undefined result. Actually gives you 0, which is probably what someone is saying in the chat.
No, it gives you 0 if you divide by infinity.
Anything is possible with Jesus. That's right. You can get, woo, we're going to take this far. You guys just keep it going. We'll check in on you later. Just load them up in the chat. We'll check on you in a few minutes, see what you come up with.
Anything's possible with Jesus.
Oh, I love it. Okay. So does that make sense? All right. So I need to not only look at the objective function, I need to incorporate the constraint. All right, great. So let's do it. So the Lagrange multiplier method is simply this. Here is my objective function. Let me, in fact, write that. This is my objective function. So that's the distance from, well, actually the square of the distance from the origin to a point on my, well, actually it's not because I haven't constrained it yet. That's just the distance from the origin. The G is the constraint. And that says that the x1 and x2 have to be such that they are on the ellipse. And that's what keeps it from going to 0 or going to infinity. The capital lambda here is the Lagrange multiplier. So we call this the augmented function. I'll use the notation f tilde. F tilde is the original f, the objective function, plus lambda times g, the constraint. So that is the augmented function. We've augmented the objective function with the constraint to give us our augmented function f tilde. That's it. Then now we do everything on f tilde just like we would have for an unconstrained problem on f. That's it. That's the Lagrange multiplier method. It's super, super straightforward. All right, so now this, this d here, d tilde, that should be an f tilde. That was my bad. So we have our f tilde, our augmented function. It's still algebraic. And now we just treat it like a regular minimization and maximization process. So I take the derivatives of f tilde with respect to each of the design variables, x1 and x2. I set them equal to 0, and we see what we get. We find out what x1 and x2 have to be in order for those two equations to be satisfied. So for this particular problem, f tilde is f, which is x1 squared plus x2 squared, plus capital lambda times the constraint, which is the equation of the ellipse, 3x1 squared minus 2x1 x2 plus 3x2 squared minus 8. Okay, Now this is our new function, our augmented function f tilde. That's the new function that we differentiate with respect to x1 and x2. All right, so these are on the next slide, but let's do these derivative evaluations. So the partial derivative of f tilde with respect to x1, well, here's an x1, so that's 2x1. No x1 here, so that term goes away. This is 6 times lambda x1 minus 2 lambda x2. No x1 here, no x1 here. So it's 2x1 plus lambda times the quantity 6x1 minus 2x2, which I hope is what I said just a moment ago. And that's equal to 0. Then we do the same thing, partial f tilde, partial x2, sorry, this one. No x2 here, so that's 0. 2x2, no x2 here, minus 2 lambda x1 plus, so if you want to see what it was like, what life in the United States was sort of kind of like in the early to mid 1980s when your friendly professor was a senior in high school, freshman in college, watch. Yes, it is an Apple TV show, so sorry, but it's good. It's called For All Mankind. So the first season last year, the premise was, what if the Russians, then of course the Soviets, what if the Soviet Union got to the moon first in 1969? How would history, so it's like this alternate history. So it's the same people like Deke Slayton and all the same NASA people, but they got there first. And how would things be different? So that was 1960s, late 1960s, early 1970s. The second season is set in 1983. So now we both, the Americans and the Russians, had bases on the moon, and of course all the stuff going on. But so it's a great show. It really is very good. But one of the great things as well is they really capture the period. My wife loves to look at, like, the styles, hairstyles, what people are wearing, but also the decor. So the lights of the era, the colors of the era. And yes, your friendly professor did wear polyester bell bottoms at one point in his life. It is a big mistake. I don't understand why bell bottoms are coming back, or have they gone out yet? Or are they still coming back? Bell bottoms were like, oh, and the big collars, polyester, scratchy, just makes my skin cringe just thinking about it. Anyway, back to our regularly scheduled. Well, let's see what you guys came up with. It seems to have stopped at 4 comments. Isn't he technically 1/3 of a whole? Oh, that is awesome! The Trinity. So yeah, figure that out. So just be 0.333 repeating. That was a good South Park voice you just did. Oh, unintentional. Okay, very nice. I'm impressed. You guys are good. Good stuff. Made my day. All right. When conversation's getting a little dry, just bring up Jesus. It's always good for lightening the mood. Anyway, okay, where were we? Oh yeah, partial f, partial x2. I think it was right in the middle of that. So partial f tilde, partial x2. No x2 here, 2x2. Then no x2 here, minus 2 lambda x1, plus 6 lambda x2 here, and that's a constant, so that's 0. And then you set that equal to 0. So 2x2 plus lambda minus 2x1 plus 6x2, which again, I think is what I said, is equal to 0. Look what we have. Look at this. Look at this. So if I simplify this a bit, there's a 2. I can factor out a 2 out of everywhere here. Look what I get. 3x1 minus x2 is equal to a little lambda x1. My little lambda is 1 over big lambda. Then the second equation is minus x1 plus 3x2 is equal to little lambda x2. Oh my, look at what we got, an Eigen problem. It's like every day we come up with some new eigenproblem. Last time I did a quadratic programming problem. Remember, we had the ratio of the quadratics, and we wanted to find a minimum. It ended up being an eigenproblem. Here again, we get an eigenproblem. So turns out this is a quadratic programming problem because everything is quadratic. It's all squared. Everything is squared. So we'll talk about that in a moment. So this is not by accident. It's not just, I didn't pick out the one problem in the entire universe that gives us this eigenproblem. Anyway, so we have an eigenproblem where A is this matrix, 3 minus 1 minus 1, 3, 3 minus 1 minus 1, 3. It's symmetric. Then lambda, and then you have your x1, x2. The eigenvalues and eigenvectors. Eigenvalues are 2 and 4. The corresponding eigenvectors, just use MATLAB or Mathematica or Python to get these, or you can do it by hand if you're so inclined. The eigenvectors are 1, 1 and minus 1, 1. Great. Again, I just got those for Mathematica or something. So what do those represent in terms of our original problem? Well, the eigenvectors are the directions of the semi-major and minor axes. One thing you'll notice, these are orthogonal. Remember, orthogonal means if I take the inner product or the dot product of these two, I get 0. 1 times minus 1 is minus 1, plus 1 times 1 is 1, 1 minus 1. Oh, I got a 2. I don't know where I got a 2 from. Plus 1 minus 1, I get back to 0. So yeah, Castle can't even count on his. Oh, that's going to be a meme. I hope no one got a picture of that. That's going to be a terrible meme. Castle cannot even count on his fingers. Yikes. I need to use my toes because in my hands I have all my Apple devices. So I have to count on my toes. Sorry. All right, anyway, so these are orthogonal, which actually makes sense, right? Because the semi-major and minor axes of an ellipse are always going to be orthogonal to one another. So these give the direction. 1, 1 is in the first quadrant, right? Bisecting the first quadrant. And minus 1, 1 is in the second quadrant, bisecting the second quadrant. So 45 degrees rotated from the XY or X1, X2 axes. All right, so that all makes sense. Then the lambdas are going to be related to the distances. They are not the distances, but they're going to be related to the distance, as you'll see in a moment. All right, so let's take a look at that. I'm going to do this very fast. The details are not important, but just to kind of complete the problem and determine which one of those is semi-major and which one is semi-minor. I don't know because I need to know the lengths. So if you go back to the original equation for the ellipse, and if I think, okay, let's take the 1, 1 direction, and I want to see how far in x1, x2 can I go, or do I have to go to get to, in this direction, to get to my ellipse? So let's set x1 to be c1, x2 to be c1. That corresponds to the 1, 1 eigenvalue. Substitute those into my equation for the ellipse, and I get 4c1 squared plus 0 is equal to 8. So therefore, c1 is equal to plus or minus square root 2. Great. So that gives me the, not the distance, but it's related to the distance. So then x1 is square root 2, x2 is square root 2. And so the length, which is the square root of the sum of the squares, well, that's equal to 2. Because I square these, that's 2 plus 2 is 4. Did that on my toes. Square root of 4, of course, is 2. So if I go along the 1, 1 direction, I go a distance 2 to get to the surface of the ellipse itself. Fine. Let's do the minus 1, 1 direction. So now the normal direction to that, 90 degrees. So now I'm going to use x1 is minus c2, x2 is c2, again, corresponding to the minus 1 and 1. Substitute those in, and I find that c2 is plus or minus 1. So x1 is minus 1, x2 is 1. I told you I was going to do this fast because it's not terribly important. You don't really need to know how to do this. I just want to make sure I complete the problem so you have some closure. And so the square root of the sum of the squares is then the square root of 2, which is like 1.4, so that's less than 2. So the semi-major axis is in the 1, 1 direction, and the semi-minor axis is in the minus 1, 1 direction. Again, that's just an example to illustrate primarily, the method of Lagrange multipliers. So I have an objective function to minimize and maximize. I have a constraint on that optimization. I incorporate the constraint using Lagrange multiplier. Then I just do the same process as always, take the derivatives with respect to each of the design variables, set them equal to 0, and then solve for the design variables. And that's it. Awesome. Bunch of remarks. As I said, this is a quadratic programming problem. Quadratic is just a fancy term for second order polynomials. And it turns out that all quadratic programming problems turn into what's called a generalized Eigen problem. A normal or regular eigenproblem is a times x is equal to lambda times x. A generalized eigenproblem has a b, has a matrix on the right-hand side as well. So in our case right here, b was just I. B was the identity matrix I. So we got a regular eigenproblem. But in general, quadratic programming problems will always result in a generalized eigenproblem. Now, if you have multiple constraints, then you just have multiple Lagrange multipliers. So say we have capital S constraints, G1, G2 through GS. You simply augment your objective function J or F or whatever you're calling it with a Lagrange multiplier times each of your constraints, all capital S of them. And then again, you just do your differentiation with respect to x1, x2 through xn, and everything else is the same. So the Lagrange multiplier method covers all the bases, takes care of all these scenarios. Now, the mathematicians amongst us will say, wait. What about partial j tilde or partial f tilde, partial lambda? Lambda is a variable, actually. Lagrange multiplier is a variable. I don't know what it is. So shouldn't we differentiate with respect to lambda? Yeah, you should actually. But when you do, and you set it equal to 0, you just get back the constraint equation. So if I take, well, we can look at it right here. If I take the derivative of j tilde with respect to lambda 1, look what I get. I get g1 minus c is equal to 0. Well, that's just my first constraint. So we don't actually do it because it doesn't give us any new information, but it does actually make sense. If you do the differentiation, it will give you, it'll reinforce the fact that your constraint has to be satisfied. So mathematically, it's all consistent and it makes sense, but in practice, it's not necessary, excuse me, to actually do, because it just gives you information that you already have. Okay, let's do another problem. We have, no, I'm not asking you, Siri. You have other issues. Do I have time to do this? 5 minutes? I don't want to rush it, but I'm going to do it anyway. No, we'll do it next time. So let's see, where are we at? So you need to grade your exams. We're going to continue this next time. This is equality constraints. We'll talk about inequality constraints as well. And then next time, we're going to focus on linear programming problems. So the objective functions and the constraints are all going to be linear equations. It's actually harder than for nonlinear for reasons that you'll see. All right, so I'll see you on Tuesday. In the meantime, you have your problem set. I don't even remember what for. 4 due tomorrow at midnight, 11:59. So hopefully you're madly working on those. Or better yet, hopefully you're done. And then we'll go from there. Take a COVID study day tomorrow on me. All right. Thanks, guys. See ya.